So main source for the forum for our technical guide is the Domestic Heating Design Guide. I have an older copy here, 2015, which is slightly out of date. So some of the figures I'm going to use today are actually amended from the later copy than this is in this guide. Looking at radiator sizing. In radiator sizing there are a series of factors, 4 factors, F1, F2, F3 and F4, and these give us values to adjust our calculated output of our radiator depending on the situation we're using. The most significant factor for this is our F1 factor, and the most interesting one from my mind after the F1 is the F2, and the F3 and F4 are quite boring. So I'm going to cover F1 and F2 in this, and I'll mention the 3 and 4 for you. If you want to know more about 3 and 4, have a look in your Domestic Heating Design Guide. Or if you request, I may do a video on it later, but it's really not that interesting. Right, so radiator sizing F1. In a catalogue, if you get one of these catalogues for radiators, these are nearly always rated at delta T 50. Now you can see in this one's a bit different. You've got 60 and 50. It doesn't bother to tell us it's delta T 50 and delta T 60, but that's what it means by T 60 and T 50 there. And you can see we've got higher outputs of delta T 60 than we have at 50. Now that's a column a lot of people don't know exists, don't know what it means, and ignore. And they'll do their heat loss calculation. They'll get a room. I'm going to use a 1000 watt radiator for this example today. And they'll go to the catalogue and they'll search down the catalogue for a radiator with an output of 1000 watts. Somewhere in here there'll be one. Not that it matters. Anyway, they'll look for a radiator with an output of 1000 watts. They'll screw that to the wall, and that's a radiator sizing done. But unfortunately it's not the case, and that radiator is probably incorrectly sized, and that would depend on a few other factors such as F1, F2, F3 and F4. Thunder's decided to strike in the middle of my video. Right, so F1. On modern systems, now let me explain delta T 50 for you to start with. So if you look at a radiator, the radiator catalogue delta T 50 is designed with a flow temperature of 80 and a return temperature of 60, which gives us a mean water temperature of 70, and the target air temperature we assume to be 20 for this design criteria. And the difference between the mean water temperature 70 and the 20 is 50. So we state the mean water to air temperature delta T as being 50 C. As we saw in the catalogue, that delta T is here. So delta T 60 is assuming a mean water temperature of 80. Now it might be possible to understand that's not really that possible, but I guess for that we'd end up with a flow temperature of 85 and a return of 75, I guess, because we're not going to be getting up to 90 flow temperatures. I'll comment on that a little bit more later as well, that delta T 60 rating. Right, so if we've got a flow temperature up in these ranges here with returns of 60, we're out of condensing range for our boiler. And this is not a setting we want to set, whether we're set at a single temperature or whether we're using weather compensation. We don't want our boiler to be running at these high temperatures or to have to run at them. If we can avoid it, what we really want ideally is for the boiler to always be as close to fully condensing as possible, and for that the theoretical target is delta T 20 mean water air temperature to room temperature, which would be a flow temperature of 50 and a return temperature of 30. Now this can be impractical in a lot of cases, and a lot of cases you're retrofitting a boiler in an older property and you don't want to be changing the radiator. But all the same, we should understand it, and we should understand how we calculate our F1 factor. Now you might want to retro calculate that F1 factor as well. You might want to look at the size of the radiators you've actually got and look at the heat loss characteristics of the building, and from that you could work out what the original design strategy was, and it may not have been delta T50, but that's a little bit more complicated. But here today we're going to just cover how to calculate the conversion factor for your radiator, so you select the correct radiator according to your design criteria. Okay, so so we call this 80-60 design. Low temperature systems target a mean water temperature to air temperature of delta T20 and flow and return delta T20. We call this 50-30 design. Different strategies can be used, for example 60-40 and 70-50. 70-50 is actually quite popular. Most of the year round at 70-50 your boiler will be in condensing range. 60-40, even more of it'll be in full condensing range, and of course the ideal that we use as a design criteria is 50-30. But these are all valid design criteria you could use, and the main controlling factor that would be the size of the radiator relevant to the room temperature. So you might actually have a room where you cannot fit a radiator big enough to use 50-30. So you might change your strategy to 60-40, then find you can't fit this radiator in the room either, in which case you would change to 70-50, hopefully not going back to the old strategy of 80-60. But let's say you went for 70-50, you would then size all of the radiators in the house based on that strategy. If you were using sort of weather compensation systems, you could mix and match a little bit more if you were using something like Evo Home. Something like Evo Home will compensate for poor design and for poor radiator selection, and you could argue that you could actually do a better design using Evo Home if you wanted to make that argument. I don't think I'd agree with it, but it's one of those arguments that would fall down more to opinion, I think. Right. Radiator charts normally show mean water temperature at delta T50, as we've already said. Now, decorative radiators and towel radiators are often rated at delta T60, and that's not usually that easy to get disclosed. And I think this is deliberately to mislead people. So your customer goes onto the internet, looks up the output, find out they want 1,000 watts, and they order one at delta T60, stick it on the wall and wonder why they're cold when they've got their boiler set to a flow temperature of 60 or 70 because they haven't got it maxed out. It gets to winter time, they just can't keep the house warm, and they're moaning about their new fancy radiator they paid a fortune for. We need to know the delta T50 for the output of any radiator we select. We need to know our design criteria. We need to make sure our radiator is sized appropriately. Right, so the F1 factor is a conversion factor to allow us to reassess the output of a radiator with an output rated at a catalogue value delta T at our chosen design delta T. So just to make sense of that, we're going to calculate a conversion factor that we will use to recalculate the size of radiator we're going to select from the chart to actually get a radiator that's going to give us the output that we wanted. So the formula for this is F1 equals the actual delta T divided by the catalogue delta T to the power of 1.24. Now if you're out in the field and you can't remember the formula, I simply remember it that these two are in alphabetical order, so it's actual over calculated, over catalogue, A, alphabetical order C. Otherwise, sometimes I can't remember whether it's a catalogue on top or the actual delta T on the top. This 1.24 value changed. So my version 2015, which is now out of date, states this to be 1.3, and in the later version, it's got it to 1.24. So currently, we are going with 1.24. So to apply the formula, we divide the actual delta T by the catalogue delta T, and we look for the square, the power of 1.24, which is 20 divided by 50 is 0.4 to the power of 1.24, and the answer is 0.321. Very nice number. So a 1,000 watt radiator will give 1000 watts times 0.23 equals 321 watts output at delta T20, mean water to air temperature. So a radiator that you used to think would give you a 1 kilowatt output, when you change your strategy to 50/30, is only going to give you 321 watts. That's obviously not going to be enough. So if we want to select a radiator with a 1000 watt output, we need to know the adjusted output to select. We use the reciprocal. To calculate a reciprocal, we divide 1 by our value. So this is 1 divided by 0.32, which was our calculated figure up here, and we get the answer of 3.115. So if we multiply our original radiator, the desired output, by 3.115, we will find it's 3,115 watts. So if we then return to our chart and we select a radiator rated for 3,115 watts at delta T50, it will give us 1,000 watts at delta T20. So I hope that helps. So think carefully about the strategy you're using for heating. And also, if you size your radiators up for any of the strategies, you can realign your flow temperatures on your system for your best economy. So the other factors, we get F2, radiator connection factor, F3, enclosure factor, and F4, paint finish factor. So working on the less interesting ones first, if you change your paint finish on your radiator, it may affect the output of the radiator, and in the SIBSI book are some factors to apply for a change of paint finish. In general practice, oil and water-based paints will give you the full output, and metallic type paints will reduce the output quite a lot, and I can't remember the numbers. Enclosure factor, so where you site the radiator, if it's in an enclosure, if it's got a shelf above it, if it's in a recess, if it's under a window, all of these factors affect the output of the radiator, and the values for those are listed in the book. So as you choose your location for your radiator, don't forget to adjust the size and output of your radiator accordingly. Your F2 factor, radiator connection factor. This is quite an interesting one. The standard is top and bottom side, same end. Top, bottom, same end. And this is common practice here in Europe. In fact, in my flat in Estonia, my connections are done this way. So the TRV is at the top of the radiator, where you can actually get to it and turn it without bending over and cricking your back, which I never appreciated until I went past 50. And now I don't want to bend down to TRVs. I really like the system. And the radiators are designed, the output of the radiator is rated for this connection method. If you connect top and bottom opposite ends, you get the better output from the radiator. This is the best way to connect for full output, but it makes very little difference. And if you connect like we do in England, we're reducing the output by going bottom opposite ends. And we need to increase the size of our radiator a little bit in order to compensate for this connection method. So it's not significant differences, but I find this one quite interesting, so I'm happy to talk about it. Okay, I hope that's clear. All of this is explained in the SIBSI Domestic Heating Design Guide. So if you haven't followed my video, get a copy of the book. I'm not sure what the latest one, I think it's 2018 is the latest one, I'm not sure. I think it's about £35. And this has all the base data, all the base information you need for designing basic heating systems. So, okay, I'm going to post this up on my YouTube channel, so don't forget to subscribe and give me a thumbs up if you're watching this on YouTube. Thank you very much.